So hi everyone, my name is Priscilla Holguin Luna, and I am a graduate student at New Mexico State University, where I work with my advisor, Joe Burchett. And today I'm going to be talking about a project that I'm currently working on with Stephanie Tonneson and Shai Ganel that I started as a pre-doctoral fellow at the CCA. So I want to couple a lot of the work that we've been talking about and hearing about to the largest scales of gaseous halos, so those of galaxy clusters. So if this is the CGM kind of environment we've been thinking of, I'm going to be taking us to a much bigger environment. And just for those who may not be familiar with these scales, for a coma-like cluster, the ICM, or the CGM, is typically on the scale of a few megaparsec. So prior work has shown that the CGM is suppressed in cluster environments. And these studies are from quasar sightlines. However, there's been some recent work that has shown H1 detections in the outskirts of clusters. These are also from quasar sightlines. And so this raises a question for us of where is this H1 coming from? Is this, stripped CGM that we're detecting? Is this actually a part of the ICM? So to look at that, we need to think about the gas in the outskirts of clusters. So X-ray emission has been detected beyond the virial radius. Now, this is a beautiful map from XCOP. This is the XMM Clusters Outskirts project. And you can see also in theory, this agrees, hot gas definitely extends beyond the virial radius. This white line here is actually denoting 2R200 for this simulated cluster. And also out around 2R200, between 2 and 3R200, we find that satellites begin to quench in this region. And we also find that CGM, the halo gas, is also being stripped this far out in some simulations. And this is some recent work observationally, just to highlight, out at 3 to 4 R200, we're already seeing, all of these are showing cluster galaxies here. You can see that the fraction of star-forming galaxies is well below what we would expect in the field for halos of the same mass. So the outer accretion shock is also, just coincidentally, something that we find in between 2 to 3 R200. And this is a cluster analyzed by Elad Zinger. This is the same cluster at different redshifts. You can see that the accretion shock locations are shown by these dashed lines. And I've highlighted here in pink the 2 to 3 R200 range. You can see that some of the shock fronts fall within that range. And so this is also supported by recent SC observations. These are observations of stacked SC profiles. And they identified pressure deficits in their pressure profiles, and these were attributed to shock locations, actually. And again, I've overlaid this 2 to 3 R200 range, and it coincidentally lines up really nicely with one of the locations of this pressure, of the deficit in the pressure profile. So the outermost accretion shock in the cluster environment is a discontinuity in the entropy profile of the cluster, and it therefore acts as a boundary of phase change in the ICM. The work by Elad Zinger has found that 40 to 70% of the halo gas is actually lost via ram pressure stripping by 2 R200. This was in simulated clusters, of course. And there's also been more recent work looking at how the CGM is affected by shock interactions, and this was in TNG 100. This is out to about 1.5 R200, and they find that stripping of the CGM is actually enhanced after encountering a shock. So this poses this question that really motivated this project of, could the accretion shock then be a mechanism that is causing quenching in the cluster environment? So here is one of the galaxies in our sample. We are tracking 441 satellites across 12 galaxy clusters in TNG 100. And we track them from a redshift of 0.5 to 0. This redshift range marks a change in galaxy cluster populations across cosmic time. There's known redshift evolution in that epoch. And our key comparisons are between what we call a shocked sample and the filamentary sample. So these shocked subhalos are ones that actually encounter the accretion shock. And the filamentary ones are ones that do not encounter the accretion shock, but they both have the same selection criteria of having to begin beyond 3 R200 and ending up within 2 R200 by redshift 0. They also must all have an initial CGM mass so that we can track that. So we find 346 filamentary galaxies and 95 shocked galaxies So per our cluster sample, there are 3 times as many galaxies from 0.5 to 0 that are entering via a filament and not interacting with this high entropy shocked gas. So typically, the accretion shock is located using a radially averaged profile, radially averaged entropy profile. This is the usual approximation we use for entropy. This here is, again, that work from ELAD showing such an example of this. However, this is neglecting the asymmetry of the shock front. And if we look at, this is one of the clusters in our sample. Each frame here is corresponding to a 60 kiloparsec slice that's centered around the core of the cluster. And you're seeing the same cluster in the X, Y, and Z plane. So while radially averaging maybe in the X would be fine, you can see that there's extremely high asymmetry in these other axes. So to account for that asymmetry, we've developed a novel approach to identifying on a satellite by satellite basis when a galaxy crosses through the shock front. And we've achieved this by calculating something we call the entropy path of the satellite. And we calculate that in every snapshot for which we track a subhalo to identify exactly when it is that the subhalo is encountering this shocked gas and interacting with it. So here's one such example of one of our subhalos. It's marked by this pink dot you can see here. And I've overlain this pink line on top of it just to give you an idea of what this path is. So it's essentially like a line of sight entropy profile that is between the satellite and the core of the cluster. And we calculate this for every snapshot, so it changes for every snapshot. So we are able to, by identifying and tracking, when a satellite passes through the accretion shock, we can examine what happens to the CGM, as well as begin to look at other interesting parameters that are typically indicative of other quenching processes. So the way we're going to do that is we're going to look at 2 ways in which satellites accrete to the cluster, right? So this non-shocked via the filamentary route, or via interacting with the accretion shock. So as a baseline, we look at the typical CGM mass of galaxies that are not falling into a halo, but are of similar mass at what, for the redshift range we're tracking around these clusters. And this is shown by these solid circles, and this is redshift of 0.5, the highest redshift that we look at. If we look at this same population of galaxies, but now at redshift 0, we see that the CGM mass doesn't evolve significantly for this. If we now want to compare this to galaxies that are accreting into the clusters, those that eventually encounter shocks, this is what they look like at a redshift of 0.5. So you can see that they're very similar in CGM mass at the same fixed stellar mass as the baseline sample. And we can also look at this filamentary sample. And looking at these, we see that particularly at some of these intermediate masses, these filaments may have experienced some prior CGM mass loss at a redshift of 0.5 relative to galaxies of similar mass that are centrals of their own halos or that later on encounter a shock front. So if we now just focus on the CGM of the galaxies that are falling into the cluster environment, this is what that sample looks like, again, of the shock subhalos at 0.5, and this is what they look like at 0. So we're seeing that shock subhalos have a 0.5 to over 1 dex change in their CGM mass for a fixed stellar mass after encountering the accretion shock and accreting into the cluster. If we now look at the filamentary sample, we see that these experience greater than 1 dex. Some of these bins are down at 0 because the CGM has been completely evacuated for some of these subhalos. So our next question was, have the filamentary satellites lost more of their CGM by the time the shock interaction is happening? And what is that time associated with the shock passing? So to look at this, we track the change in CGM mass. We call it delta M CGM. This is just the percentage, right, of the CGM mass that is lost across specifically the shock interaction. So we matched satellites in the filamentary sample and the shocked sample. At their closest matches, they have to be at the same redshift, have within 0.5 dex of the same CGM mass and stellar mass, and they have to be within 15% of each other's R over R200 value at their matched redshift. And so these are the preliminary results for that. And we're only including here shock satellites which experience mass loss. There is a very small portion, about 15% of our sample, that actually experience a CGM mass growth after interacting with the shock. And as you can see, the CGM mass loss at the shock crossing are comparable for filamentary and shock satellites. So this is where I leave you with that. So what does that mean? There's kind of two scenarios we're seeing here, right? The shock interaction is either slowing down the CGM mass loss rate, perhaps, after it interacts with the shock, that coal gas supply is cut off. And then so this is a slower kind of process of CGM removal through starvation. Or it could be that the satellites are accreting in filaments, experience a faster CGM removal due to the actual filaments themselves because of their density or because these galaxies are moving faster. So this is, a more rapid ram pressure stripping of the actual CGM itself. Oh, sorry. And that is where I leave you. The accretion shock is one such mechanism that actively contributes to this multi-phase nature of the ICM and can thus act as both a catalyst and consequence of galactic evolution.
More just a kind of clarification question of how are you defining the mass of the CGM as
Yeah.
the halo?
So we define all the gas particles that are beyond twice the stellar half-mass radius and gravitationally bound to the halo. That's what we use as the CGM mass.
Okay. And I'm wondering if some is still bound but further away than that, or is that something you looked at?
Yeah, we haven't. We do want to do kind of in a follow-up, not for the paper that we're going to be publishing for this work, but we do want to do a follow-up of some of the more interesting systems. I track all of those parameters for all of the satellites, so it's, 95 times 6 plots to go through. Don't really fit in a paper easily. But for those most interesting systems, we are thinking of doing, like the gas density to see if there's actual evidence of stripping and compression and stuff in the CGM and in the nearby gas in the ICM. Yeah.
Yeah, very, very nice stuff. I don't know if I may have missed this, but did you also look at the star formation rates of these satellites?
Yeah.
Before and after they pass through the accretion shock?
Yeah, so we are doing that. That's something that we're actively working on right now. We're unsure, so a lot of the filamentary sample don't have star formation rates by redshift 0, but we don't want to just have that be, like a zero value, and so we are trying to decide how to, on a binned basis, include that as kind of like that at the, this is the upper limit of like the last value that the star formation rate was at before we no longer have that information tracked for that satellite. So I do have some plots of that, and we can look at those offline together if you want. But I wouldn't trust some of the bins that have some crazy error bars on them right now.
Don't know if Amanda wants to come up.
Yeah, do you also separate the effects like a satellite has lost this gas due to overshooting or preprocessing before falling into the,
Yeah, so we want to fold that into the analysis for sure. It'll be very easy to look at, which galaxies are falling in within another halo, if they're already part of a halo falling in, and so they might have pre-processing. When it comes to overshooting, we have looked at the closest pericentric passage for a lot of the shock subhalos. They don't actually, overshoot or anything, but a lot of the filamentary sample does. So, yes.
So, just on focus. I was just trying to work out how you could tie this to observational data. And it's really hard because you just don't know whether they've gone through the shock or not yourself. So
yeah. So the observational work I mentioned in the beginning, we're going to be submitting a paper at the end of this next month, tracing H1 and oxygen 6 from the core clusters of 6 R200, and I found this tentative excess around 2 to 3 R200, which is really what motivated a lot of this work, because we think it might be a signature of the accretion shock of just a buildup of H1. And so aside from that, though, when it comes to actually measuring, for the satellites, maybe someday.
Well, thank you. Let's